All right. Hi, everyone. I hope you can hear me and see my screen. My name is Dimitri, and today I want to talk a bit about design patterns, which is a very kind of 90s topic, something that we've kind of stopped discussing along the way. And I think if you take 10 or 15 years back and if you went to a job interview back then, people would definitely ask you questions on design patterns, but now it's kind of somewhat forgotten. So what I wanted to do is to give a few examples of why design patterns show up in our daily C++ programming life and how you can actually implement them. And I wanted to start with something that I hear quite a lot from many different developer teams, and that is the idea that a lot of companies have their own string classes. And you might be wondering, well, why on earth would anyone want their own string class instead of std string? Well, let me give you a very simple example of why you'd want something like that. Let's suppose I have a string with hello world, something like this. I'll put a few spaces in between just for the fun of it. Now, let's suppose, for example, that I want to have, let's say I want to make the string lowercase, and then I want to split it by word and then print the length of each word. It's a very simple operation, but unfortunately, if we're talking about the standard library, you don't really get this functionality at all. The standard library doesn't provide you a way of making the string lowercase or splitting it by word, or, well, it does give you the length in a kind of confusing way. So typically, if I wanted to do this just using the standard library stuff, I couldn't. I would have to use at least the boost string algorithms to get the lowercase and the split. So to do that, to do what I want, I would type something like the following. I'll make the string lowercase, so I would use to lower copy of the string, and then I would prepare a vector of where I would have the separate words, and then I would call boost split, which is another function from the boost string algorithms. I would specify the parts to put the data into. I would specify my lowercase string, and then I would specify the delimiter that I want to split on, and maybe some additional arguments as well. So typically, this is what it would look like if I wanted to do it just using the standard form, and I would have each of the parts in my parts, and I would maybe see out the length of the appropriate part, like so. So this is fine. I mean, it works. We're going to see it run in a moment. It's absolutely no problem. The only problem with what I've just written is discoverability. Well, there is another problem here that I have 3 zeros in between. So the length of hello is 5, the length of world is 5, and then I have a bunch of zeros because there is another argument here which happens to be optional, and as a consequence, if I want to get rid of those zeros, I would have something like boost token compress on just to get rid of those extra zeros. But at any rate, the problem with all of this, even though it does work and it works just fine, is that ultimately it's non-discoverable, meaning that unless you know that there is a function called to lower copy, unless you know that there is a function, and these are global functions, by the way, called boost split, you're not going to be able to even find out that these operations exist. And certainly, if you are coming from the Java world or .NET world, you would expect the string class to have a split function. You would absolutely require it, and this is why we build adapters. So an adapter is essentially just a way of getting the interface that you want instead of the interface that you're given. So let's build a string adapter. I'll have a class called string with a capital S, and here I'm just going to essentially encapsulate an ordinary string. So I'll have it in here, and then I'll generate a constructor maybe to initialize the string like so. And then, of course, what I can do is those APIs that I've been using as global functions, what I can do is I can take them into the adapter class. So instead of having all of this, which is okay to some extent, I guess I could have them in here. So if I want, for example, to lower copy, I would have a capital string. Notice I'm returning a capital string, my own string, and I would have a function called to lower copy, which would be const. And here I would simply return a string constructed from boost to lower copy, taking the string that we're encapsulating here. And similarly for the split function, if I want to split something and get a vector of these capital strings, I would have something like the following. I would have a vector of a string called split, and I would have a const string delimiter, maybe with a default value. So I might have the empty space as the default value. It kind of makes sense, and I think that's the default in other programming languages. Here I would have a vector of lowercase string called parts. I would call boost split, split like so, providing the parts, providing the string to split on. I would use boost is any of to actually it's any of like so with the delimiter, and I would maybe also get rid of those empty tokens. So I would use boost token compress on like so, and then I would return a vector of capital string constructed from the vector of these parts. So I would simply say parts.begin and parts.end like so. So essentially what I've done is I've taken these global functions, these global APIs, and I've moved them into my adapter. And now I can change it. I can make it capital string here, and then the operations can essentially be done one after another. What is it saying here? Oh, there is a typo apparently. I don't think there is a typo. Delimiter. Is it? Is there really a typo renamed to? No, I think I'm all right in here. Okay, so essentially I now have this capital string and actually limit. Yeah, limiter. So let's do it the smart way. Delimiter. Funny. Okay. No more complaints from the system, obviously. So now, if I want to split the appropriate parts, what I want to do is I can just write this as a single for loop. So I can say for auto W, let's say if it's a word, in, and then I can do the following. I can do s dot, and you'll notice that after the dot I get code completion. So I get some information about the kind of things that my particular string is capable of doing, like turning the string lowercase and then splitting it on a word. And I can all do this in line, and here I can see out W dot, and now I want the length. Now, one of the things if you take like a developer from the street and you tell them that std string has both a length and a size, the weird thing about all of this is that it's confusing. So the std string has a size and a length, and if you take somebody who's not very familiar with C++ and you ask them, what do you think these actually mean? They would probably tell you something like the following. They would tell you that length is the number of characters and size is the number of bytes that the string occupies, which we know is not the case. We know that these things are identical. So in the process of constructing my adapter, I can actually determine my own API for how I want to get length. And certainly length is not a behavior. And having the name length, I don't like this, because I think that length like this implies that the string has some sort of behavior called length. Instead, I prefer get length, and this is a very simple implementation. So I would do s.length here, for example, and so I can actually output this at this location, get length. End line. Okay, so what have we done? I mean, we haven't really changed, the structure of the universe. We haven't delved into STL to actually modify these things. And in actual fact, the implementation of Boost's global functions like split, for example, is a good example of kind of a non-intrusive design, in a sense that you don't break the open-close principle, which we'll talk about in a moment. But essentially, instead of jumping into the STL and getting it this way, what you end up doing is you end up kind of having these global add-ons. The problem with the globals is discoverability, and we've solved that problem by building the adapter. And as a result, we can certainly run this and get the same output as before. But the key thing here is that it's usable, meaning that somebody who is working with a string with a capital S would actually get the APIs that they might expect, like to lower copy, for example, right inside code completion. That having that list after the dot is kind of crucial, because it basically tells you everything that you need to know, and it is impossible to provide. I mean, one of the ideas is to provide a code completion list for every global function which takes a string as a first argument. So you might say, well, this might work. But in actual fact, if you look at split, in split, the string isn't even the first argument, it's the second argument. Not to mention the fact that there is a temporary being introduced here that you have to make a separate statement for, and it's all a bit confusing. And so the approach here is you build an adapter which just the things that you want, and certainly there is some overhead to having all of these calls, and not much. There isn't much overhead, but there's certainly a certain amount of overhead. But the end result is that you get just the APIs that you're looking for, and this is why people actually build these sort of things. So even despite the overhead, we end up building lots of these adapters because the default API, I'm sad to say, but the default API of std string is somewhat lacking, and this is why you end up using Boost and that sort of stuff. Okay, so this has been a very small example of how a design pattern occurs in the wild. Let's take a look at something else. Let's take a look at the builder design pattern, which is something that's used to essentially construct objects. So if you think of a scenario where, let's say you're building some sort of web server, for example, so you want to output HTML. You can certainly go ahead and start outputting HTML just using an string, for example. So let's suppose I want a list of 2 words, let's say hello and world. So let's have these words, and I'll have hello, and I have world as well. So I have these 2 words, and I want to have them as part of an HTML list. The kind of simple approach is you just make an string stream, let's call it OSS. You add the fact that it's an unordered list. Let's do a line break here, and then for each of the words that you're given, so auto W in words, you add something else to this list. You might add a couple of spaces. You might add the actual list item, then the word itself, then close the list item, maybe do a line break at the end, and at some point you close out the whole thing, and then you sort of see out oss.str like so. Something to that effect. I mean, it works just fine until you actually want to build something more complicated, and until you want to actually have this situation kind of manageable. We're certainly getting the output that we want, but it's kind of not very pretty, shall we say. So at some point you may end up actually building object-oriented structures for storing this entire thing, so that it's kind of easier to build. So you may end up with some sort of structure like an HTML element, for example. So you would have an element which would have a name, and you would have the text, and you would have maybe a vector of children, HTML element, let's call them elements. And you might also have some formatting information. So you might have, let's say, the indentation size. We'll use that in a moment. So the HTML element, you can certainly have an HTML element where the constructor does absolutely nothing, but you can also have an HTML element where the constructor actually initializes, let's say, the name and the text. So I'll use clines functionality to generate those. And then, of course, at some point, once you've built up this tree, because it's essentially a tree, because an element can have other elements to infinity, what you need to do is you need to have some sort of output. You want to output this stuff as text, and I will spare you the actual code for pretty printing this stuff, because I'll just paste it here from the GitHub repo. So now we end up with an object-oriented structure, and what this means is we can already start kind of building it up, in the sense that we might have a root element called an unordered list, and in this case we can give it the name ul, like so, and absolutely no text. And then for once again each word in the collection of words, we can say ul dot, and in this case it's elements dot push back, and we can make an element which contains it's HTML element. So you might have an HTML element of type li, list item, which contains the word w, and at some point you can certainly take ul and once again str. So we haven't made a dedicated builder here, but the what we have done is we've made everything object-oriented. So it's now more logical, in a sense, to actually construct this HTML element. But we can sort of take, and here is the output, by the way. So you can see we're getting pretty much the same thing. However, we can make it even better by essentially having a dedicated component for building up these structures. So if we want to build up a list, we might as well build an HTML builder. Now, what this HTML builder is going to do is it might take the name of the root, for example. So I might have HTML builder which takes the root name, and we might say assign the root name. We're going to have an HTML element that we're actually building up. So here it is, element, let's call it root. So you make this builder, and then we can have a function for actually adding the children. And the function might be something like this. So first of all, I'll make it void. So we'll have a function called add child. And this function takes, let's say, the child name and the child text. And all we have to do here is we make a new HTML element and we add it to the children of this element. So essentially we make HTML element E with child name and child text. And then what we do is we say root.elements dot and place back and sort of move the element over, and that's pretty much it. Now, a consequence of this, as soon as I learn how to spell, because I see that I've made a couple of errors here. They're going to go away in just a moment. But the consequence of all of this is that we can further improve this example. So now we have a dedicated component for actually building stuff. We have an HTML builder called builder, and this builder might be building an unordered list. And then when we want to actually add a couple of children, I'm going to just, instead of going over the list, I'll just add the elements manually. So you would have builder.addChild with the child name being li, list item, and the text being hello, and you do the same thing with the text for world. And then, of course, once you're done building up the entire thing, you want to, once again, print it out. And in this case, it would be builder.root, something like that, builder.root.str. And it works in a similar fashion to what we've just had a couple of times already. The difference is that we now have a dedicated component. We can make an improvement, and here is the output, by the way, same as before. We can make a small improvement by making the builder fluent. Now, a fluent interface is when you can chain the calls which make up something, when you can chain the calls which make up an object. So here, instead of turning void, I can return an HTML builder reference, and I can simply return star this. And the consequence of this is I can now delete this part, and you can see that I can call builder.addChild and then addChild once again and again. And if we had other functions in addition to addChild, different kind of build-up functions, they can all be strung together, because each of these functions would return a reference to self, a reference to the builder itself. Now, let's suppose that we want to have the builder as the only way in which you can construct an object. In this case, what you would do is you would typically take the constructors and you just make them private first of all. So you would make maybe a private section here, just hide the constructors, and this way nobody can really make an HTML builder anymore. You can see that there are complaints here because HTML element is now private. So obviously you need some sort of improvements to that, in the sense that you now need to have you need to have a friend class HTML builder. And by the way, we need to forward declare HTML builder, seeing how we are doing everything in a single file. So I'll put HTML builder in here. You'll see why in a moment. Because essentially what the situation we have right now is that you cannot really construct the HTML element anymore at all. The only way you can go is through the builder. And certainly, yes, you can work through the builder, but there is another way. You can sort of hint to the user that they're actually meant to call some sort of static build function. So here in the public section, we can make the following. We can make a static function which will return a unique PTR called HTML builder. We'll make the function build like so, and it would take a root name, and it would simply call the constructor of HTML builder. So you return make unique of HTML builder, root underscore name. By the way, to get make unique, I think you need something like C++1y. If you have 0x here, it's not going to work on all systems. So we return essentially an instance of the builder class right from the class that's being built up. So the consequence of this is that we can now do the following. So instead of making a builder like this, what would happen typically is the following. You would have the HTML element itself, so HTML element : and then you would call build with the argument of an unordered list, and then you would do dash greater than, and then do all those add child calls. Remember, the add child calls return references, so that's why there is a dot here. You can have them return pointers instead, and it would be a dash greater than. Now the question is, well, how do you output stuff? Because we still have this builder root, but there is another way of doing this, kind of the icing on the cake, and that is to simply return the root as an operator to HTML element. So essentially what I can say on the builder itself is I can say, whenever somebody asks you for an HTML element, why don't you return one? Why don't you return root? Like so. And the end result is that you can write the following. You can write HTML element E equals, and then do this entire call, and this will actually be valid because after all these invocations, remember this is a Fluent interface, it returns a reference to an HTML builder. After all these invocations, you would end up essentially constructing an HTML element, and here what we can do is we can say e.str, and hopefully this runs. Right, fingers crossed. Oh, we should really be getting the same kind of stuff as before. And here it is. Okay, so this is an example of a Fluent builder, but many programming languages nowadays, they go one step further. They say, oh, by the way, if you want to build HTML, we'll give you a nice looking DSL-like structure right inside the programming language. Now, amazingly enough, you can also get this kind of construct in C++, and I'll show you how in a moment. This is something that is present in languages such as Groovy. So let's get rid of this, and we're going to once again make some HTML, but we're going to make some HTML using initializer lists of all things. So once again, I'm not going to bore you with the details of the implementation of the tag class that we're going to be using. It's similar to what we had in the HTML element in the sense that we have the name, the text, we have a bunch of children. I also have a bunch of attributes as a vector of pair of strings. We have some pretty printing here, and that's pretty much it. Let me close this out. However, the key thing that we're going to construct here is a bunch of protected constructors. Protected. There we go. So essentially, I'm not going to allow anybody to actually manufacture this tag because it's a top-level construct that we're going to specialize through inheritance, but it is going to have a bunch of rather useful constructors. So let's actually see if we can generate some of them. I'll just jump in here, generate a constructor. So we'll have the name and the text as one of the constructors, but the other constructor is going to be a bit tricky. And no, I don't want it public. I want it protected specifically. So the other constructor is going to take the name and the bunch of children. So I may as well write it myself. Const string name and const vector of tag children, and also initialize the name and initialize the children. Okay, so we have these protected constructors. The question is, why do we bother with all of this? And the answer is that we're going to inherit from this tag. So essentially, if you're talking about HTML, you have very well-defined tags like a paragraph or an image. So why not specify those explicitly? And that's exactly what we're going to do. So if I want a paragraph, I can say that a paragraph inherits from a tag, and then I will have an explicit constructor called P, which takes just the text. And by the way, I should probably be using just the ordinary code generation stuff for it. As you can see, if I use code generation, it actually asks me which base constructor I want to call. And the answer is, well, at the moment I'll call the first one. The only thing is that we don't really want to take name as an argument, because we know that the name of a paragraph is P. So I may as well remove this part, and I just replace this with P, because that's a predetermined kind of tag. And similarly for the other constructor, let's go and generate a constructor once again. Now you'll notice that in the base we have a vector of stuff. However, I can do a small trick here, and we already know the name, and but we do want to pass the children. The only thing is we want to pass the children as an initializer list, because, well, that's the beauty of modern C++. Initializer lists are going to give us that magic that you'll see in just a moment. So what I'm going to have here instead is I'll make an initializer list of tags called children, and then for the initialization, for calling the base class, I know that the name is paragraph, so that's P, and we leave the children as is. So there's a bit of magic happening here, because you're taking an initializer list and you're passing it into something which is expecting a vector, and this is absolutely fine. So we have a paragraph. Let me just build up another construct. Let's build an image. So img is going to be a tag as well, and in this case we'll have a constructor which takes just a URL. So I'll use the code generation, even though in this particular case it's not so useful, I'm afraid, but we'll still call the base as before. I'm going to replace the actual constructor arguments here, because all I want for an image is the URL of that image. So here is the URL. Now the tag, we know the tag is img, and the image contains absolutely no text whatsoever. It does have an attribute though. So here in the constructor I can say that attributes dot and place back, and I'm going to add an attribute. Let's do make pair. So the src of the image is equal to the URL that we provide. Okay, so what just happened? Why did we build all of this? Essentially, we built all of this to construct a strongly typed DSL specifically for HTML. And to actually use this, we can use this as follows. So I can, for example, cout, and I can cout a paragraph. And notice the curly braces here. So I can make a paragraph which contains an image which has the URL of some site, PNG, for example. So this, what I've written just now, and line, is completely valid C++. Amazingly enough. So this may look like a DSL, but it's really not. It's just using initializer lists to essentially construct these kinds of notations out of the fact that we've taken the base class and we specialized it so that you can either take a text or you can take an initializer list of tags. So a paragraph can contain an image, and that image becomes the one and only element of this argument. So a very small trick, which once again, if you are building some sort of structured data, this kind of groovy style builder can actually help you define these nice little DSLs. So just a small syntactic trick that you can do in C++. Sticking with this idea of builders, though, I do want to show something a bit more complicated, and that is the idea of multiple builders working to build a single object. That's going to be a bit more complicated, and we're going to have more classes and more constructs here. So bear with me as I go through this and try to construct this one. So essentially, the idea is that let's actually make a new class. So I'll make a C++ class. Let's call it person, for example. So let's have person in here. Now, the person class, let's suppose that there are two distinct aspects of person that we want to build up. So we're going to build up some address information that a person has. So you might have, let's say, street address, postcode, and city. But we also have some information regarding employment. So a person might have a company name, they might have a position, they might have annual income. Let's put a default value in here as well. So you might say, well, why don't we just make a single builder which kind of builds everything? But in actual fact, we can be even smarter about this whole thing in the sense that we can build multiple builders in actual fact. And to do this, once again, what I'm going to do is I'm going to hide the constructor. So I'll hide the constructor, make it private, but I will have some public stuff. Now, in terms of the public stuff which I'm going to expose a builder. So let's have a static function called create, which will return a person builder. Person builder create. Sorry, there should be no round brackets here. So the question is, well, what is this person builder? Given that we're going to have several builders, what does person builder actually look like? So for this, we're going to add yet another class. And this time around, I'm not sure we actually need to have not sure we need the CPP for. Let's have both the header and the CPP. So we'll have person builder. Now, person builder is not just an ordinary builder for personing. Instead, it's something that exposes different builder facets. And different builder facets are essentially aspects of the overall builder. By the way, I see that some of the files here are grayed out. Let me just briefly add those to the CMake list. So that's person builder .hpp as well. Okay, so that's gonna take a while to actually spool. But meanwhile, let's jump into person builder. So person builder is this wonderful class which, instead of building a person, what it does is it gives us different sub builders which can build up the different person information, like for example the address information or the employment information separately. There are two different aspects to this person builder thing. So essentially it's going to be rather complicated. So we're going to have the person that we're actually building up. That's all right. That's what we're building. That's what we're doing. But in addition to that, it's going to have some protected members, and this is where things might turn a bit weird. By the way, if you're wondering why some of the kind of code assistance that's supposed to be showing up is not showing up, it's because we're in the process of reloading the CMake list and getting all those extra files in here. So essentially the faceted builder is a bit sophisticated because in addition to the object being built up, in the protected section it also has a reference to this person being built up. And it also has an explicit constructor, it's called person builder, which actually takes a reference to a person and initializes that reference. And you might think that this is somehow redundant, but in actual fact it is necessary for our little demonstration, and it has some public members. Finally we're going to have some public elements, and specifically we're going to have a default constructor. So we'll have a person builder which initializes the person reference to the person that's being built up. Again, a bit unusual that, and it will also expose those builder facets. So remember our goal, and by the way, yes, we do need the person.h here, but our goal in all of these cases is to provide functionality for building up the address information and provide functionality for building up the information regarding a person's employment. So we'll have two builders here. We'll have a person address builder, and the function is going to be called lives, and we'll have a person job builder, and the function will be called works, like so. Right, I do need to have a couple of fixes here. You can see that there's a certain number of complaints because essentially we're trying to get into person, whereas person is kind of private and wouldn't really allow itself to kind of doesn't allow other classes to get into it. So we need to fix that first of all, and this is done using friend classes. So here down below I'll have friend class person builder, friend class person address builder, and friend class person job builder. That's what we're going to call the builder which builds up the job part. So in terms of the forward declarations, I think we need to forward declare the person builder here, and that's pretty much it, I think. Certainly, yes, we do need the string, and I'll just get using namespace std in here as well. So that solves all the problem. In this case, obviously, we haven't got an implementation for create, so that is something that I'm going to generate right now, and we'll see what's going on in terms of the actual creation of the person builder. So bear with me, person builder. Right. So the person builder create is rather boring. We just make a new class and we return that. There is absolutely nothing of interest that's going on here. However, the interesting part happens in the person builder.cpp, because essentially if we look at lives and works, you'll see that we're referring to some classes which do not exist. That kind of explains the error. And by the way, let me generate those because I'm getting really tired of all these this red code. So we'll have a person address builder. May as well have it header only. So let's have person address builder, and let's also have once again header only person job builder. Right. So these two classes are going to be building up the address information and the job information as well. And the question is, well, what do they look like? Because it's all getting reasonably complicated. So let's start with the person job builder. And now person job builder actually happens to inherit from person builder. And this is the piece of magic. So the sub builder happens to inherit from the builder which exposes it, which means it has access to the object that's actually being built up. And it also explains why we made all those crazy constructors. So let me type def person job builder. I'll type def the person job builder itself because I want to have a fluent interface. So we'll have a constructor. I think we actually need to add it to CMake lists, of course. So let me do that. So that's person job builder and person address builder. So let's have that. Now we need a constructor which actually takes a person reference and initializes exactly that. So for that, I'll just write this myself for now, given that the CMake lists file is reloading. So we have a person job builder which takes a person reference called person, and then it calls the base class with this reference, and that's why we have that protected constructor, so that whenever you make a sub builder, you're actually referring to that one and same object that you're building up throughout the entire thing. So the constructor is here, and now we can make a fluent interface, and yes, this does require an include of I think person builder.hpp. That's pretty much all that we need. We are going to include this later on, but yeah, the errors are gone. So essentially, if you want to say that a person works at a particular company, you make a fluent interface, so that's where the self ampersand comes from, and you say at, and then you take the company name. So you take the company name, you say person.company name equals company name, and then you return star this. So you make this a fluid interface, and the same goes for the other parts of your employment information that you're trying to build up. So if you want to say that the person works at a particular position, you say as a, you specify position here, and you say person dot position equals position, and return star this again. And if you want to specify the earning, you say earning int annual income, maybe income, and you once again you say person dot annual income, income equals annual income, and you return star this. Okay, so that's the job builder done, and we also have the address builder. That's for building the address information. So it's also fairly obvious. I will spare you the actual details and simply paste the code from the repository. I think we also need a string for this one. Do we need string for the other one as well? We might. I think we might, but then again, I'm not so sure. Okay. Anyways, we have well, we do need a reference here, I think. or maybe not. It doesn't really matter. So anyways, we now have two builders which build up a person, and they are exposed through these. They are exposed through the person builder, which essentially gives out whichever sub-builder you're actually interested in. So that might be a sub-builder for the address or for the job. So I'm going to forward declare those as well. So I'll have person address builder and also person job builder, like so. So essentially, when you kind of interact with this, you interact with these functions called lives and works. And yes, these are some redundant round brackets here. So we have person address builder and person job builder. They'll turn green at some point. Now let's talk about how this entire thing is actually used, because we want to construct a person at some point. So how do we do it? Let's go into our main. So essentially the idea is that we want to write something like the following. First of all, I want to say person p equals, and yes, that requires a header, person : create. So the create call here is what I want for the creation of the builder. So as you call create, you get your builder, and you can start calling things on the builder, meaning that if I want to specify the information about where a person lives, I can say .lives, lives like so, and then I can say .at and specify where the individual actually lives. Because remember, at the end of create, what you get is you get a reference to a person builder. Let me open that up, and person builder has functions called lives and works. So we get those, and if I kind of complete the picture, so to speak, so that you get the feel for what we've been trying to achieve, it would look something like the following. So essentially you would have the call to create, and then you would have the sub-builders. I suppose I can make them a bit prettier by kind of moving things around and having them kind of aligned like this. But the end result, I'm going to try compiling it. I hope I got all the headers in the right order, so to speak. Let's see what we get here. So, person builder is not a member. Oh yes, the one thing we didn't do is we didn't do the operator. Remember this function for making the converting operator. So that's kind of the icing on the cake, so to speak, for our person builder implementation, in the sense that somewhere here you can say operator person, and you may as well move out the person that we've been working on. Like so. So this should be okay, I think. And even if it's not, the demo that's up on GitHub is perfectly fine. I won't dwell on this. Let's see what are we getting here. Person builder is not a member of person. Okay. So this is something that should probably go into person builder.cpp. So somewhere in here. And let me see if I need anything else in this, because I think I need plenty of includes. I think I need the one thing that you might want is hold on. Did we? Oh, we hold on. Yeah, this cannot work yet because we need to implement lives and works, and this is where certainly some of the magic happens. Because these implementations, what they do, let me just paste them in here, what they do is they expose the different builder facets. So they expose the person address builder, and they expose the person job builder initialized with the person that we're kind of referring to in here. So the consequence, let me just jump into main and I'll explain what's kind of happening here. The consequence is that lives and works, essentially they let you jump from one builder to another, and thereby you can initialize the address, for example, and at any point in time during this fluent invocation you can jump to the job builder and then continue working with the job builder. So that's the point of the kind of multifaceted builders. Right, now the final thing I want to show, seeing how time is short and we probably won't have time to cover the specification pattern, is the maybe mode, which is another interesting kind of construct. So I'll get rid of some of the things that we've built here, and you can download the actual sources from GitHub if you want to see how the entire thing works. And I'll just sort of jump ahead and show you the maybe implementation. So essentially, C++ is not a functional programming language. However, the cool thing about it is that you do have functional plurals. You do have things like std function, and as a consequence of that, you do have some of the capabilities for building monads, which are design patterns in functional programming. So let me give you a very small and very contrived example of the maybe monad. I'm not going to use the classic notation, the classic terminology, but I am going to kind of show you how some of the things are solved in the functional world. So let's imagine that we have a struct for a person, and that person may or may not have an address. So address pointer address equals null PTR. I'm deliberately using pointers here. You might be using something else like smart pointers or references or something to that effect. Now let's suppose that this address that I'm defining also has a house name. So if you're living in an ordinary house, you might have just a street name and number, but if you're a rock star and you bought yourself a castle, that castle probably has a name, but you might not have one. So that's a null PTR once again. Now the problem is, what if I want to write a function which actually prints the house name? So given a person, I want to print their house name. I would write something like print house name, which takes a person pointer P, and then if I want to do this correctly, I have to make all these null checks. So I have to say if P is not equal to null PTR and P address is not equal to null PTR and P address house name is not equal to null PTR, then and only then can I actually print out the address. So then I can do P address house name. I can do it like this, and line. So the maybe monad essentially tries to encapsulate the very idea of checking for the presence or absence of something. In this case, the presence or absence of a value, because you might not have a value. You might just have a null PTR instead. So the question is, how can we encapsulate this so that we don't do these checks ourselves? And the maybe monad is one of the ways that you can actually do this. So let me show you how you can construct one. Essentially, what we do is we make a template class. So let's make a template type name T struct maybe, and this is something that we're going to build up. So let me put this in here. Now the maybe monad itself is just something which keeps a context of where we are in the process of drilling down into person, because what's happening as we get into person, then into address, then into house name is the process of drilling down into an object-oriented structure. And the consequence of that is that we have a context, we have a location where we are at the moment. So here I can specify T star as the context that we're in. T is a template argument, so it can be virtually anything. Now what I want to do is I want to be able to construct this object. So I want to be able to construct an instance of maybe using the context, just initializing the context to the variable, context, like so. Nothing particularly magical happening here. Now, if I want to make a maybe out of P, I cannot simply write something like maybe M of P, because type inferencing, unfortunately, doesn't work yet on the maybe. I'm not going to be able to compile it. So what happens typically, what we do quite often, is we make these functions which actually help us get that type inference. So I'm going to copy the actual declaration here and just forward declare it like so, and then I'll have a template function which template type name T. So I'll have a function which returns a maybe of T, and it's called maybe with a small m, which takes the context and simply returns a maybe of T with the context. Now, why did I just do this? Why did I waste so much of your time. And the reason I did this is that so I could write something like the following: auto z equals maybe of p. So now I can write maybe of p without having to specify any template arguments in here. But all I've done is made a maybe, and I now want to drill into the object. I want to drill into the address and then into house name, and only print it if it's not null. So how can I do this? Well, one of the things I can do here up above is I can define a function called with, which is going to be template type name tfunc. So notice that the type argument here is a function. It's not just a variable. So we'll have a function. I'll have auto return type. No idea why it's indenting like this. Auto, and let's call it with. So we're going to take this function as the evaluator. And here we'll have all the fun stuff. So essentially, we may or may not have a context which is in a null state. If the context is null, which means we cannot really drill into our structure at all. We're not allowed to do it. But if the context is okay, we can call the evaluator function on the context and drill into whatever structure we're investigating. So if the context is not equal to null PTR, then what I'm returning is a maybe of the evaluator function on the context. Otherwise, I'm just returning null PTR. That's all that's happening here. And as a consequence, we can jump into our print house name thing, and we can do a couple of invocations. So if I want the address, I will say the following. I will say with, and here I take a function. So I may as well do a lambda here. So I'll have a lambda which captures nothing. It takes some argument x, in this case it's a person pointer, and I return x dash greater than address. You'll notice that there is no help here, there is no code completion at this point. It's a bit difficult for the system to figure out what's going on. And I can repeat the process by drilling into the house name, because I've now changed the context to being inside the address, and I can get the house name. And finally, if I have the house name, or if I'm in a null state, I want to try and print out what the house name actually is. So for this, let's make another function. Let's have template type name func auto, let's call this function do, which also takes a tfunc action. So it's not an evaluator. It doesn't operate upon the context. It just does something. So as long as the context is not null PTR, I can call this action on the context, and then I can return star this. We don't change the context here. We just stay as we were in this, that same maybe. So let's have it as func here. Okay, so the final piece of the puzzle is that at this point we can do a do, once again taking a lambda which auto x, and here x would either be, well, here x, assuming that we invoke this, x would be the name of the house, so we can see out star x and line. Okay, so we've constructed the monad. The question is, how can we actually use this? A typical example is, let's suppose I have just a person P, and I call print house name, providing a pointer to P. What would happen is the context would originally be set to the pointer to a person, which is valid. However, as we go into with, what would happen is we would check the context against null PTR, and because it's null PTR, the rest of the entire invocation chain, the rest of this whole thing will be a no-op. Nothing, absolutely nothing will happen at this point. Whereas if I continue to building up person, so for example, I will say, I'll state the address, and I'll also specify the house name, and I'll be sure to delete them later on, then we are actually going to print this out. We're actually going to get the house, because throughout the entire invocation chain, we'll drill first of all into address, then we'll drill into house name, and those things are not null at any point. And as a result, this comparison with not null will always succeed, such that we'll always call the drilling in function, which is provided as a lambda. So let me actually try to compile this. I hope this this works and gives us the required output. Hooray! Amazingly enough, we get the output. We get my Picasso. And if you try to step through this code, you will see that the process of drilling down happens inside the lambdas. So essentially, we set the context to a person, and then this lambda sets the x2 pointer to a person, and provided that it's not null, we get the address, and we set that as the context. Then we get the house name, we set that as the context. And because the context is not null here, whatever this lambda actually does in fact get invoked. So essentially, this implementation of the maybe monad has encapsulated the very idea of drilling into some complicated structure. And this kind of implementation, of course, is not limited to checking for null. I've encapsulated the idea of the presence or absence of something by a null PTR, but you can use a boost optional or std optional instead, or you can use, it's amenable to using shared pointers or whatever, so you can adapt this approach to actually work for you. So I think this is going to be the last thing that I'm going to mention today. Let me just take a look at the comments here briefly. I'll try to answer most of the comments in the blog post that we'll do together with the recording. But essentially, let's see. Somebody's wondering where I'm pasting this from. I'm actually pasting this from the GitHub repo. And just in case you forgot, here is the address. So it's github.com/Nestor Design Patterns webinar. That's where you can find all the source code for this entire webinar, including the specification pattern, which I simply did not have time to talk about. And there's going to be plenty more examples later on in there as I kind of build up on this. So in closing, what I want to say is that I have a bunch of design patterns in C++ courses up on Pluralsight. Plus, I'm working on a book called Modern Design Patterns in Modern C++. I'll let everyone know as soon as that's finished. It's going to take some time. And I thank you very much for joining this webinar and hope to see you again soon.